properties. What we will be having these many topics in fluid mechanics. The first topic is fluid properties. Then we talk about the statics of the fluid. Then kinematics, the analysis of the moving fluid without considering forces. And then it is the fluid dynamics. Fluid dynamics of ideal flow, fluid dynamics for the real flow, and then the multi-pipe system, and finally the boundary layer theory. Compound pipe is internal flow, multi-pipe system, and boundary layer theory is for external flow. These are the various, or these are the most important topics of fluid mechanics. So we will try to cover properties, statics and kinematics today. Hi Shubham, Kiran. Yes, these topics we will cover in part 1 and the remaining topics we will cover in part 2. All right. And if you have any doubt, anything to ask, you can always raise your concern through the comment section. And keep on talking to me so that the class should not become monotonous and you enjoy the session. All right. So let us start. The reference books. So many students keep on asking me what are the best reference books for fluid mechanics. In my opinion, the Fluid Mechanics Fundamental and Application by Eunice Sengel for concept clarity is very beautiful book. And for numerical practice, you can go with the Subramaniam, Fluid Mechanics and Hydraulic Machine Problem and Solution for numericals. For numericals, you can go with the Subramaniam, and for theory, you can refer, or whatever book you are referring, that is also fine. But if you have not studied from any of the book yet, then you can refer these books for theory as well as numericals. All right. Yes, that is also fine, Pudina. No problem in that. Okay, Madhuamsi, definitely. We will try. I will try. There are faculties actually dedicated for these sessions for different subjects. So that is a concern actually. The availability of the teacher as well as the dedicated faculties are there for different subjects. But definitely I will try. If possible, I will try to take some sessions on thermodynamics sometime. Actually, what exactly is the fluid? Before we start, let us discuss about the fluid. 3 important properties make the substance a fluid. What are the important properties? The substance which deforms continuously, a substance which deforms continuously on the application of shear or tangential force, no matter how small is the magnitude of tangential force. So that makes the substance a fluid. If the substance is having a deformation, angular deformation continuously, whenever we apply the tangential force on the substance, no matter how much is the magnitude, how small is the magnitude of tangential force, once the substance satisfies these 3 conditions, the substance will be a fluid. Example, liquid and gas. So whenever we apply a shear force or the tangential force to the fluid, then what happens? There is a deformation, angular deformation. So there is a velocity profile developed. There is a velocity profile getting developed. Whenever we apply the shear or the tangential force to the fluid, there is a velocity profile developed. Yes, in GATE examination, there is no surety. Sometimes a particular subject can be asked for more marks. Sometimes a particular subject may not be asked for that many marks. So it is highly uncertain. So you should prepare each and every topic thoroughly. You never know from which portion there might be a question, from another portion, important portion, there might not be a question. Yes, this year's heat transfer was surprising. Yes, definitely. So whenever we apply the shear force, there is a velocity profile developed. So there is a condition called as hydrostatic condition. Do you guys having any idea about hydrostatic condition? Whenever we do not apply shear stress, then there is no relative, there is no deformation. The condition is called as hydrostatic condition. The fluid is said to be in hydrostatic condition. And in hydrostatic condition, the more circle reduces to a point, no shear stress, the more circle reduces to a point. Right? That is all about the definition of a fluid. Liquid and gas constitutes the fluid. The properties of the fluid include the density. What is density of the fluid? Density denoted by rho, that is mass upon volume, mass per unit volume. The unit is kg per meter cube. Standard unit is kg per meter cube. Volume can also be written in terms of liter. 1 liter is equal to 10 to the power minus 3 meter cube or 10 to the power 3 centimeter cube. That is the conversion. You should know how to convert liter into meter cube or vice versa. Density of the liquid remains constant. For the liquid, density remains constant. For a gas, density is a function of temperature and pressure. For a gas, density is a function of temperature and pressure. How it varies? As the pressure of the gas increases, density also increases. As the temperature of the gas increases, density of the gas decreases. I hope you know about this. You can remember from P is equal to rho RT. That is the ideal gas equation. From here we can say rho is directly proportional to pressure and rho is inversely proportional to temperature. That is how it varies. Density, mass per unit volume. Another property is weight density or specific gravity. The next property is specific gravity or relative density. What is specific weight density or specific weight? What is weight density or specific weight? That is denoted with gamma. That is weight per unit volume, or we can write it as rho into g. That is weight density, rho multiplied by g. What is the unit? What is the unit? Newton per meter cube. The force can be written as in dyne also. 1 dyne is equal to 10 to the power minus 5 Newton. Another unit is kgf, 9.81 Newton. Weight per unit volume. Another property is relative density related to density. That is called as relative density or specific gravity. What is specific gravity or relative density? Generally denoted by S. What is the relative density? Hi Jabir, welcome. How are you? The weight density varies with temperature, pressure and location. The weight density varies with temperature, pressure and location. Specific gravity is the ratio of density of the fluid to the density of water at 4 degrees Celsius. Or we can say specific gravity of the fluid upon specific gravity of water. Sorry. Gamma for the fluid divided by gamma for water. All these terms are having same physical significance. It is unitless. All these properties are having same physical significance. What is that? All these gives us the information about the lightness or the heaviness of a substance or of a fluid. All these terms give us the information about the density is giving us the information about the lightness or heaviness of a substance. Whether it is mass density, weight density or relative density, it gives us the information whether a fluid is light or heavy. Right? These are 3 types of densities only. So there is no different significance Pudina as such. But because we sometimes require the acceleration due to gravity also, weight also required, that is how it is defined. The difference between mass density and weight density is similar to the difference between mass and weight. Yes, Pudina. Location becomes important in understanding, in analyzing the fluid. So that is why when the location comes into picture, we define the weight density. And because we compare the fluid with respect to some standard fluid, and then the relative density comes into picture. Relative density is the relation of the density of the fluid to the density of the standard fluid, which is water at 4 degrees Celsius. The next important property is viscosity. Viscosity gives us the information about thickness or thinness of the fluid, whether the fluid is thin or thick. Viscosity is all about the thickness or the thinness of the fluid. What is viscosity? It is the resistance to the flow, resistance to deformation, or resistance to relative motion. Yes. It is having, the first is less viscous, the second fluid is more viscous. More viscous means thick, less viscous means thin. Viscosity gives us the information about the thickness or thinness of the fluid. It is the measure of internal resistance between the adjacent fluid particle in relative motion. I have already told you, what I have already told you is, whenever we apply a shear force, tangential force on the fluid, there is a velocity profile developed. U becomes a function of y. The flow is in x direction. The flow is in x direction, and normal to the flow, the velocity varies. So velocity profile developed, and if we take the adjacent fluid element, we will observe that the rate of shear strain is equal to velocity gradient. Du by dy is equal to d theta by dt. Du by dy is equal to d theta by dt. That is the important relation we developed. Du by dy is the rate, is the velocity gradient. D theta by dt is rate of angular deformation or rate of shear strain or strain rate. And now the Newton's law of viscosity is defined. According to Newton's law of viscosity, which gives the defining equation for coefficient of viscosity, according to Newton's law of viscosity, the shear stress developed is mu into rate of angular deformation or mu into du by dy. That is the mathematical expression for Newton's law of viscosity. What is d theta by dt? Rate of angular deformation, or we can call it as rate of shear strain, or we can call it as strain rate. What is the unit? What is the unit? Du by dy is the velocity gradient. Velocity gradient. This is obtained from u as a function of y given. For velocity profile linear, for linear velocity when u is a function of y is given, we can find out du by dy velocity gradient. What is mu? Here, what is mu? Mu is called as coefficient of viscosity, or we can call it as dynamic viscosity, or we can call it as absolute viscosity. Coefficient of viscosity, dynamic viscosity or absolute viscosity. स्टार्टिंग से कर रहे हैं अमीर, तो देखते हैं डायनेमिक्स के चांसेस कम है, स्टैटिक्स और काइनेमेटिक्स कंप्लीट कराने की पूरी कोशिश करूंगा मैं. सो म्यू is called as coefficient of viscosity, dynamic or absolute. Mu is independent of temperature. Sorry, mu is independent of density. Mu is independent of density. Mu is not a function of density of the fluid. That is why it is called as absolute viscosity. How to define mu? The shear stress required to produce unit rate of shear strain. How to define mu? Tau upon d theta by dt. The amount of shear stress required to produce unit rate of shear strain is called as coefficient of viscosity. If the velocity profile is linear, in case of linear velocity profile, du by dy is equal to v by h. that is not a function of y, is constant. So the modified expression for Newton's law of viscosity, tangential force per unit area, shear area is equal to mu into v by h. It is not a function of y. It is constant with respect to y. That is the Newton's law of viscosity modified expression for Newton's law of viscosity if the velocity profile is assumed linear. For linear velocity profile, tau is ft by as is equal to mu v by h. What is the unit of viscosity? Can you let me know what is the unit of viscosity? Dynamic viscosity mu. In SI unit, it is Newton second per meter square, or we can call it as Pascal second or kg per meter second. हाँ अभिषेक, Pascal second or kg per meter second. In CGS unit, in CGS system, what is the unit of viscosity? इसको लिख सकते हैं डाइन सेकेंड पर सेंटीमीटर स्क्वायर और ग्राम पर सेंटीमीटर सेकेंड. डाइन सेकेंड पर सेंटीमीटर स्क्वायर. जब ये दो फ्लूइड है, अलग अलग फ्लूइड है, तो दोनों में अलग अलग अप्लाई करेंगे न्यूटन्स लॉ ऑफ विस्कोसिटी. दोनों की विस्कोसिटी अलग अलग होगी, दोनों में अलग अलग न्यूटन्स लॉ ऑफ विस्कोसिटी अप्लाई होगा. कन्वर्जन आना चाहिए आपको. 1 पास्कल सेकेंड इज इक्वल टू 10 पॉइज, और वी कैन से 1 पॉइज इज इक्वल टू 10 to the power -1 पास्कल सेकेंड. What is the value of dynamic viscosity of water? Dynamic viscosity of water is 10 to the power -3 Pascal second. 10 to the power -3. Clear? कन्वर्ट कर सकते हैं आप. उसके अलावा दूसरी एक प्रॉपर्टी होती है, दैट इज कॉल्ड एज काइनेमेटिक विस्कोसिटी, ऑल्सो कॉल्ड एज मोमेंटम डिफ्यूजिविटी. हीट ट्रांसफर में हम उसको मोमेंटम डिफ्यूजिविटी बोलते हैं, न्यू से डिनोट करते हैं. मोमेंटम ट्रांसफर एबिलिटी ऑफ द फ्लूइड मॉलिक्यूल्स, म्यू बाई रो. व्हाट इज द यूनिट? इसमें इससे बोल सकते हैं कि काइनेमेटिक विस्कोसिटी इज इनवर्सली प्रोपोर्शनल टू डेंसिटी. काइनेमेटिक विस्कोसिटी इज इनवर्सली प्रोपोर्शनल टू डेंसिटी. Unit of kinematic viscosity, SI unit or MKS unit, meter square per second. What is CGS unit? CGS unit क्या होगा? सेंटीमीटर स्क्वायर पर सेकेंड, और स्टॉक 1 मीटर स्क्वायर पर सेकेंड इज इक्वल टू 10 to the power 4 स्टॉक. हाँ, रेस लगाइए कौन पहले करेक्ट आंसर देता है. कंपटीशन की भावना होनी चाहिए सब में. 1 स्टॉक इज इक्वल टू 10 to the power -4 मीटर स्क्वायर पर सेकेंड. ये कन्वर्जन आना चाहिए, राइट? वेरिएशन ऑफ विस्कोसिटी विद टेम्परेचर. विस्कोसिटी इज गवर्न्ड बाय 2 फैक्टर्स. कौन कौन से फैक्टर होते हैं? व्हाट आर द 2 फैक्टर्स? One is cohesive force, which dominate in case of liquid. Another is ये सब दुश्मन है एक दूसरे के. Another is molecular momentum transfer or molecular collision, which dominate in gas. So gases के केस में cohesive force dominate, liquid के केस में cohesive force dominate करता है, force of cohesion. Gases के केस में molecular momentum transfer और molecular collision. So this is how in liquid, as the temperature increases, viscosity decreases, and in case of gas, by increasing the temperature, viscosity increases. And for a gas, dynamic viscosity of a gas is directly proportional to under root of its absolute temperature. Kinematic viscosity of a gas is proportional to T to the power 3/2. Very nice, Abhishek. Well done. T is the absolute temperature, which must be in Kelvin. T is the absolute temperature, it must always be in Kelvin. What is the kinematic viscosity of water? That is 10 to the power minus 3 upon 10 to the power 3. That is 10 to the power minus 6 meter square per second. That is the kinematic viscosity of water. Then based on viscosity, the fluid can be divided into two parts, Newtonian and non-Newtonian fluid. Fluid can be classified as Newtonian and non-Newtonian. Tau is equal to A into du by dy to the power n plus b. That is the general expression. Based on the value of a, b and n, we can define Newtonian, non-Newtonian fluid. The C is having n is equal to 1 and b is equal to 0. C is, which fluid is C? We can say for D, n is greater than 1, b is equal to 0. For B, n is less than 1, b is equal to 0. And for A, n is equal to 1, but b is non-zero. These are various fluids. And this is, let us say, E, this is F. This is called as rheological behavior. The relation between shear stress tau and d theta by dt, rate of angular deformation. Can you just let me know? Curve A stands for Bingham plastic. A is for Bingham plastic. B is for pseudoplastic. B is for pseudoplastic. C is for Newtonian. C is Newtonian and D is dilatant. E is ideal fluid and F is ideal solid. This is called as rheological behavior. मेन जो फ्लूइड का क्लासिफिकेशन ये है, यहां से दो और क्लासिफिकेशन बनाए जा सकते हैं. Two more classification can be done like this and this. Here n is greater than 1 and b is non-zero. Here n is less than 1 and b is non-zero. This is thixotropic lipstick and this is rheopactic. Thixotropic and rheopactic gypsum. The next property is compressibility. The next one is compressibility. What is compressibility? Denoted by beta. Compressibility is compression ability of the fluid. What is the unit? Meter square per Newton. It is the reciprocal of bulk modulus K. K is given by change in pressure per unit change in volume per unit volume. Or we can write it as rho into dP by d rho. The unit is Newton per meter square or Pascal. That is bulk modulus. The reciprocal of bulk modulus is compressibility. So beta is equal to 1 by K. That is d rho upon rho dP. And based on beta, if beta is equal to 0, it means rho is constant. Such fluids are called as incompressible. Incompressible. Liquids are incompressible. And if beta is not 0, density will not be constant. So such fluids are called as compressible fluids. Gases are compressible. ये formula. Coefficient of compressibility. This is called as coefficient of compressibility. Beta is called as coefficient of compressibility. Coefficient of compressibility. The next important property is surface tension. Two properties are very important. One is viscosity and another is surface tension sigma. It is the property of the liquid interface. Surface tension is the property of the liquid interface or property of the liquid surface, denoted by sigma. The surface tension is due to strong cohesive force between liquid surface molecules. To overcome the downward tendencies, all the liquid surface molecules develop a strong cohesive force with each other. So the whole liquid interface appears like a thin elastic film in tension. That is called a surface tension, which can resist small forces. So sigma is a function of temperature. It is a function of temperature. As the temperature increases, molecules move away, cohesive force decreases, so sigma also decreases. As the temperature decreases, cohesive force increases, so surface tension increases. That is how surface tension varies with temperature. सरफेस टेंशन की वजह से जो फोर्स डेवलप होता है दैट इज कॉल्ड एज सरफेस टेंशन फोर्स एफएक्स व्हिच इज द टेंसाइल फोर्स. सरफेस टेंशन फोर्स इज टेंसाइल, प्रेशर फोर्स इज कंप्रेसिव. Surface tension force is tensile, which is acting normal to the common line of interface and in the plane of the liquid surface. These are the properties of surface tension force. So sigma can be defined as Fs per unit length of the common interface, or we can write it as the amount of work required per unit change in surface area. What is the unit of surface tension? Change in surface area. What is the unit of surface tension? Newton per meter or joule per meter square. These are the unit of surface tension. Newton per meter or joule per meter square. Both are correct. The amount of work required per unit change in surface area or surface tension force per unit length of the common interface. These are some of the application of surface tension. Pressure in a liquid drop. Delta P, that is inside pressure minus outside pressure, is given by 4 sigma by D, or we can call it as 2 sigma by R. D is the diameter, R is the radius. D is the diameter, R is the radius. Pressure in a soap bubble, delta P, because there are two interfaces, 8 sigma by D or 4 sigma by R. There are two interfaces. There are two interfaces. That is why it will become twice of 4 sigma by D. Pressure in a liquid jet, delta P is equal to 2 sigma by D or sigma by R. In a liquid jet, R is very, very less compared to L. So these are the application of surface tension. For an air bubble, what is the formula? For an air bubble, what is the formula for delta P? Air bubble is similar to liquid drop. Air bubble is having only one interface. It is having only one interface. Air bubble is having only one interface. And that is why delta P is equal to 4 sigma by D or 2 sigma by R. For an air bubble, it is 4 sigma by d or 2 sigma by r. Air bubble is similar to liquid drop. There is a difference between soap bubble and air bubble. Air bubble is having only one interface, whereas soap bubble is having two interfaces. All right, clear? The next property is capillarity. What is capillarity? The rise or fall of a liquid in a small diameter tube. Diameter should be less than 5 mm. Inserted in the liquid, which is due to surface tension, is called as capillarity. Capillary rise is due to less cohesion. Example is water and glass. And capillary fall is due to more cohesion. If cohesion is less than adhesion, then it is called as wetting liquid. The liquid is called as wetting liquid, and the contact angle theta is less than 90 degree. For cohesion to be less than adhesion, the liquid is wetting liquid. Contact angle theta will be less than 90 degree. Less than 90 degree. And for cohesion greater than adhesion, the liquid is called as non-wetting liquid, and theta is greater than 90 degree. So here it is the wetting liquid. Water is a wetting liquid for glass. Mercury is non-wetting liquid for. If we talk about meniscus, it will give concave meniscus. It will have concave meniscus like this. It will have concave meniscus like this. And for cohesion greater than adhesion, it will give rise to convex meniscus. Like this. This convex meniscus. And to calculate the amount of the height to which the fluid will rise or fall, that is H. What is the formula for H? Capillary rise or capillary fall? 4 sigma cos theta upon rho into G into D, rho fluid. This is the formula for capillary rise or capillary fall. Rise or fall. If we get H positive, it will give rise to capillary rise. For negative value of H, it will give rise to capillary fall. H for narrow slit is equal to half of H for capillary tube. Clear? ये कुछ स्टैंडर्ड रिजल्ट्स है. फॉर प्योर वाटर थीटा इज इक्वल टू 0 डिग्री, cos 0 is equal to 1, so H will be maximum, that is 4 sigma upon rho into G into D, rho of water into G into D. For normal water, theta is 22 degree, which is less than 90 degree, so cos theta will be greater than 0, positive. Cos theta will be positive. So H is positive. So there will be capillary rise. For mercury, theta is greater than 90 degree, 132 degree. It is greater than 90 degree. So cos theta will be less than 0, negative. So H will be negative. So capillary fall. These are some of the results. Narrow slit का मतलब है, narrow slit का मतलब है there are two parallel plates, large parallel plates like this. ये है narrow slit, इसमें fluid rise करेगा. There are large parallel plates which are kept like this, parallel plates ऐसे रखी हुई है, that is called as a narrow slit. ये ऐसे दो प्लेट्स रखी हुई है. अभी हम कैपिलरी ट्यूब की बात कर रहे थे, ट्यूब की जगह प्लेट्स हो, then it will be half of capillary tube. The last property is vapor pressure of the liquid. What is vapor pressure of the liquid? The pressure developed or exerted by liquid vapor in phase equilibrium or saturation with its liquid at a given temperature. The pressure developed by the liquid vapor, this is called as the pressure exerted by these liquid vapors. These are the liquid vapor. The pressure exerted by the liquid vapor in phase equilibrium with its liquid at a given temperature is called as vapor pressure. This is called as vapor pressure. Or it can also be defined as the saturation pressure of the liquid below which liquids gets converted into vapor. अगर vapor pressure ज़्यादा है तो more is the number of vapor molecules. So we can say vapor pressure is directly proportional to vapor molecules. More is the number of vapor molecules, more will be the vapor pressure. So we can say when the vapor pressure is high, the liquid is called as volatile liquid. The liquid is high vapor pressure, liquid is called as volatile liquid. Because of evaporation and condensation, Jabir, there is a continuous evaporation of the liquid molecules from the surface and there is a condensation of vapors converting into the liquid. When the phase equilibrium achieves, when the phase equilibrium get achieved, then at that moment the pressure which is developed by the liquid vapors is called as vapor pressure. That is why the term vapor and pressure of the liquid is called as vapor pressure. So it is also defined as the saturation pressure of the liquid below which liquid gets converted into vapor or liquid boils or evaporates. Boiling of the liquid or evaporation of the liquid take place. Yes, automatically. Yes, Jabir, automatically. Because of collisions. Because of vibrations. The liquid gets converted into vapor from the surface. And due to collision, the vapor gets converted into liquid. That is a continuous and automatic phenomena. Evaporation and condensation are continuous and automatic phenomena. So when the liquid pressure becomes less than the vapor pressure, the evaporation of the liquid will take place. And due to evaporation of the liquid, there is a problem developed which is called as cavitation. So when the cavitation happens, when the liquid pressure becomes less than the vapor pressure, the liquid boils or the vapor bubbles form, and these vapor bubbles are carried away from low pressure region and their sudden collapse. You can see the animation. This is how cavitation happens. Their sudden implosion generate extremely destructive high pressure waves in the flow, which leads to noise, vibration, erosion, and reduces the performance of turbines and pumps, hydraulic machines, turbine or pump. So we do not want the cavitation to happen. So to avoid the cavitation, liquid pressure should not fall below the vapor pressure. Liquid pressure should always be above the vapor pressure. Liquid pressure should always be above the vapor pressure. Yes, in underwater missiles, cavitation is intentionally developed. In torpedoes, cavitation is intentionally developed. What is ideal fluid? When do we call the fluid to be ideal? Who will tell? What is the ideal fluid? That covers our first topic, that is fluid properties. What is ideal fluid? Bataiye quickly. Everyone, please do let me know, what do you understand by ideal fluid? When do we call the fluid to be ideal? The fluid is called ideal when the viscosity of the fluid is 0, when the compressibility of the fluid is 0, when the surface tension of the fluid is 0. These are the three properties which make the fluid ideal. No. Madhuvamsi, I am talking about the fluid. Whenever we talk about the fluid properties, these properties of the fluid must be 0. These properties will decide the fluid to be ideal or not. Jabir, you are giving the definition for ideal flow. There is a difference between ideal fluid and ideal flow. Whenever we say ideal flow, I will talk about that. Ideal flow की बात करेंगे. Now let us move to the fluid statics. Let us move to the fluid statics. All the important links are mentioned in the description box. After the session, please go through the description box once so that you will find the important links for downloading the free ebook. And please guys, do like, share and subscribe the BYJU'S YouTube channel. Do like and share this session so that it reaches to maximum students and everyone get benefited. So let us move to the fluid statics. When the fluid is in hydrostatic condition, when tau is equal to 0. Hydrostatic condition. The most important is Pascal law. In case of static fluid, we apply the Pascal law. Head आ गया. थोड़ा break दिया मैंने relax करने के लिए. The pressure at a point in a static fluid is equal in all directions. That is the statement of Pascal law. Or even in moving fluid, even in flowing fluid, static pressure remains constant, or static pressure remains same in all the directions. That is statement of Pascal law. Another statement of Pascal law, external static pressure, it is always about the static fluid or static. Static word is important for Pascal law. The external static pressure exerted or developed on a fluid is transmitted uniformly throughout the fluid in a horizontal plane. Hydraulic press works on the principle of Pascal law. Hydraulic press. According to hydraulic press, P1 is equal to P2. P1 and P2 are equal. So we can say F1 by A1, the normal force per unit area, is equal to F2 by A2. That is the expression used in hydraulic press, hydraulic ram. The most important statement of Pascal law is this, the third one. Any 2 points or 2 or more points at same elevation in continuous mass of same static fluid will have same pressure. These are the 4 conditions. Out of these, if any 3 conditions are getting satisfied, then the 4th one will also be true. That is the corollary of Pascal law. For an example, if we take a horizontal plane and if we take point 1 here, 2 here, so P1 will be equal to P2 according to Pascal. P1 and P2 will be equal because points are lying at the same elevation. Points are part of the continuous mass of single fluid. Points are part of static fluid, and they will definitely have same pressure. If we draw another line here, 3 and 4, will P3 and P4 be equal? Will P3 and P4 be equal or not? They will not be equal. Why? Because continuous mass condition is getting violated. Same elevation condition is there, static fluid condition is there, but continuous mass condition is not getting satisfied. Because if we join 3 and 4 from the top, we are moving in multiple fluids. If we join 3 and 4 from the bottom, we are moving in multiple fluids. That is why the continuous mass condition is not getting satisfied. That is why they will not have same pressure. So Pascal law is not related with the geometry or area of the tube. Whether A1 is equal to A2 or A1 is not equal to A2. The cross-sectional area might be same, the cross-sectional area might be different. It does not matter, but P1 will be equal to P2. P1 and P2 will be equal. That is the Pascal law. That is all about the Pascal law. I hope it is clear to everyone. Please give me thumbs up. Please make some noise if it is clear up to this point. Then we define absolute pressure and gauge pressure. Absolute pressure is the pressure which is measured with respect to absolute zero. This is the absolute zero or absolute vacuum. The pressure measured with respect to absolute zero is called as absolute pressure. If you are sitting here, then you will measure the absolute pressure. The gauge pressure is the pressure measured with respect to local atmospheric pressure. Local atmospheric pressure is also called as barometric pressure. Barometric pressure. The pressure which is measured by the barometer. So the relation between these three parameters. आपका question क्या है? What is your question? Tejas Shekhar, what did you ask? Please write again. क्या मेरे को तो पता नहीं आपने क्या क्वेश्चन लिखा है. नहीं. कोविन, it is applicable for multiple tubes as well. Pascal law is applicable for all the static fluid everywhere. Where is the question? अच्छा, यही आप ही का क्वेश्चन था क्या? Coven, it is valid for multiple fluids as well. The only thing is the conditions which I have mentioned. Any three conditions must get satisfied. Then the fourth one will also be correct. Any three conditions must get satisfied. Then the fourth one will also be correct. That is called as corollary of Pascal law. If only two conditions getting satisfied, then the remaining two will not be true. The remaining two will not be true. I am still waiting for Shekhar's question. आया तो नहीं आपका question? Clear? Shall we proceed further? So the relation between absolute gauge and atmospheric pressure is given by this expression. Gauge pressure can be positive or negative. हाँ, हाइड्रोस्टैटिक पैराडॉक्स भी बताएंगे. Absolute pressure is sum of atmospheric pressure plus gauge pressure, or we can say gauge pressure is equal to absolute minus atmospheric. But atmospheric pressure should always be local one, which the barometer measures, because the atmospheric pressure varies with location and also with weather condition. All right. Then the hydrostatic law. According to Pascal law, pressure is not a function of x and y. Pressure in a horizontal plane remains constant. That is the Pascal law. In a static and single fluid, static and continuous mass, static and continuous fluid, pressure in a horizontal plane remain constant. According to hydrostatic law, pressure varies in vertical direction. The variation of pressure in vertical direction. Actually, Tejas, we cannot 100% sure unless we know the number of sheets. So we cannot comment on that whether rank less than 500 will be fine to get aerospace engineering. It depends on so many factors actually. the number of sheets as well as the toughness of the examination, and how many of the students are not preferring to do MTech from IITs. If more number of students are going into PSUs, then you might get. So dP by dz is equal to rho g, or dP by dz is equal to minus rho g. That is the hydrostatic law. For incompressible fluid, if the fluid is incompressible, rho is constant. We can say from this hydrostatic law, we can get P is equal to rho into G into H, pressure at a depth H from the free surface, or we can write pressure head given by P by rho G. That is called as pressure head. H is the depth from the free surface. Pressure head can be calculated from P by rho G. Kevin, for real gas, I don't know the formula, but one thing you must know, that the variation of pressure with height or z is exponential. For real or ideal gases, the variation of pressure is exponential. For the gases, the variation of pressure is exponential with height or depth, whereas the variation of pressure is linear in case of incompressible fluid. For the constant pressure, we can use the conversion of one fluid column into another. We can find out the pressure head of one fluid, and we can convert pressure head of one fluid into another. If pressure is constant, we can write rho1 H1 is equal to rho2 H2. Or we can write S1 H1 is equal to S2 H2. That is the formula to be used for converting one fluid head into another fluid. For an example, there are two fluids, one is rho1, another is rho2. And if we attach a piezometer, H1 is the height, H2 is the height for second tube. And the pressure P1 is equal to P2. For P1 is equal to P2, this is the pressure P1, this is the pressure P2. For P1 is equal to P2, we can say, for P1 is equal to P2, we can say rho1 G H1 is equal to rho2 G H2. These are the formula to be used for converting one fluid column into another, or the pressure head of one fluid into pressure head of another fluid. Manometer is the pressure measuring device, pressure measuring instrument, based on the balancing of the fluid column due to pressure difference. If we take, this is the initial level, let us say, this is the initial level. As long as the pressure is same, the level will be same. This is the manometric fluid rho m. When we attach the left limb to the pipe, there is a decrease of manometric fluid in the left limb. There is a rise of manometric fluid in the right limb. And according to the constant volume of the manometric fluid remains constant. So we can say A1 is the cross-sectional area of left limb, A2 is the cross-sectional area of the right limb. So A1 into A is A2 into B. Or we can say, if the cross-section is circular, then we can say D1 square into A1. A is equal to D2 square into B. And X is equal to A plus B. That is the manometric fluid deflection. That is called as manometric fluid deflection. For A1 is equal to A2, X is equal to 2A is equal to 2B. For A1 is equal to A2, X will be equal to twice of A or twice of B. Next is pressure equation. That is very, very important by using the Pascal law and hydrostatic law. Pascal plus hydrostatic law. We can write the pressure equation. There are two methods. One is called a jumping method. कैसे यूज करेंगे? Try to understand this. Let us say the manometric fluid deflection is x. This is the manometric fluid deflection, and the height of pipe, this is y. Density of manometric fluid rho m. Density of the flowing fluid is rho f. So we will jump from one point to the another point. We can start from point P. P. This point will also have the same pressure because the continuous mass, static fluid, same elevation. We are moving in downward direction plus rho f into g into x plus y. Then we can jump from this point to another point in the right limb. These 2 points are having same pressure according to Pascal law. Then we are moving in upward direction, minus pressure decreases with height, pressure increases with depth, minus rho m into g into x will be equal to PATM. That is the pressure equation. This is the absolute pressure. Gauge pressure will be equal to rho mgx minus rho f into g into x plus y. This is how we can write the gauge pressure in the pipe by using the jumping method. Another method is called as datum line method. We draw a horizontal line in such a way that the point lying on the horizontal line must have same pressure. This can be taken as the datum line. The manometric fluid deflection is x. The manometric fluid deflection is x. The height of the pipe, this is, let us say, y. So this is point x, this is point y. Px is equal to py. According to Pascal law, px and py will be equal. So how to write px? Start from point P. P plus rho f into g into x plus y, that is px, is equal to PATM. We are moving in downward direction, so pressure increases, so that is why plus rho m into g into x, this is py, and that is the absolute pressure. If we want to find out the gauge pressure, absolute minus atmospheric is gauge pressure. You will get the same result, x minus rho f into g into x plus y. This is datum line method. For single column manometer, yes, yes, Covin, as long as there is a fluid and static fluid, Pascal law will be applicable. In vacuum also Pascal law is applicable. Single column manometer, in case of single column manometer, A1 is very, very large compared to A2. So in case of a single column manometer, this is how single column manometer is. This is the initial level. There is a fall of liquid. There is a rise of liquid in the right limb. Let me call it as this H2. This is delta H. So A1 and A2. So for single column manometer, A1 into delta H will be equal to A2 into H2. That is called a single column manometer. For inclined single column manometer, A1 into delta H is equal to A2 into L. What is L? If it is inclined single column manometer, like this. So this is angle theta and L is, this distance is L. So where L is equal to, theta is the angle of inclined line with horizontal. Where L will be equal to, what is L? Or where H2 is equal to L sine theta. So sensitivity is given by 1 upon sine theta. H2 will be this. This is H2. H2 is equal to L sine theta. 1 upon sine theta is sensitivity, that is L by H2. For inclined single column manometer, sensitivity is given by 1 upon sine theta, that is L by H2. Some formula for fluid in a rigid body motion. For fluid in a rigid body motion, one formula is del P by del X is equal to minus rho AX. For fluid moving like a rigid body, del P by del X is equal to minus rho AX. Del P by del Y is equal to minus rho AY. Del P by del Z is equal to rho into G effective. These are the formula. Z is measured in downward direction. Downward. And G effective will be equal to G plus minus A. Yes, Abhishek, only formula revision. Only formula revision. Question नहीं होंगे पुदीना. Only formula revision in today's session. When G and A are in opposite direction, so G effective will be equal to, then G effective will be equal to G plus A. When G and A are in same direction, this is A, this is G, then G effective will be equal to G minus A. From here, these are the formula for rigid body motion. For horizontal acceleration, AX, we can write dz by dx is equal to tan theta is equal to AX by G is equal to delta H by L. This is the formula. For AX to be maximum without spill, then delta H should be maximum. That is equal to capital H minus small h. Twice of capital H minus small h. For maximum acceleration without spill, it is independent of density of the fluid. This expression is independent of density of the fluid. For vertical acceleration, we will use this expression. For vertical acceleration, so pressure is equal to rho into G effective into H. Pressure at a depth H is rho into G effective into H. The next topic in fluid statics is hydrostatic force. Hydrostatic force on a plane surface. If the plane surface is having an inclined position, theta is the angle of inclination with horizontal. The formula for hydrostatic force is rho F into G into A into X bar, and the depth of Cp from the free surface HCp is given by X bar plus Ig by Ax bar sine square theta. For vertical, theta will be equal to 90 degree. If theta is 90 degree, the formula for hydrostatic force, that can also be written as average pressure into area. Average pressure into area. Average pressure into area. Because the pressure varies linearly with depth. So theta is equal to 90 degrees. Sine 90 will be equal to 1. So that is why the formula for HCP is simply X bar plus Ig by X bar. For horizontal surface, theta is equal to 0 degree. So sine 0 is equal to 0. So HCP is equal to X bar. These are the formula. But you need to understand the significance of A is the area of the plane surface. What is A here? A is the area of plane surface in contact with the fluid. A is the area of the plane surface in contact with fluid. What is x bar? X bar is depth of centroid of the plane surface from the free surface. Depth of centroid of plane surface from the free surface. Rho F is the density of the fluid. What is P average? Average pressure is the pressure which is developed at G. That is rho into G into x bar. That is the average pressure. And what is Ig? Here Ig will be equal to area moment of inertia of plane surface about its centroidal axis, which is parallel to the base. Parallel to the base. That is called as Ig. And theta is the angle of inclined surface with horizontal. Surface with horizontal. These are the formula which are applicable to the plane surface. Hydrostatic force on a plane surface. For curved surface, we analyze in two ways. Horizontal component is calculated separately. What is horizontal component? Take the vertical projection. Take the vertical projection. So the horizontal component FH is equal to hydrostatic force on its vertical projection area. What is the horizontal component of hydrostatic force? Total hydrostatic force is equal to the hydrostatic force in vertical projection area. IG standard figures का पता होना चाहिए. For a rectangle, IG is LBQ by 12. For a triangle, BHQ by 36. For a circle, it is pi by 64 d to the power 4. And if it is irregular geometry, that IG will be provided to you in the question. So IG find out karna will not be a task. In FM, it will not be asked to calculate the value of IG. IG will be provided to you directly or indirectly. Hydrostatic force on its vertical projection area, and its line of action will pass through the CP for the vertical projection. So FH is equal to rho F into G into vertical projection area into x bar. X bar is the depth of centroid of the vertical projection for vertical projection. If this is the vertical projection and G is the centroid of the vertical projection, x bar will be this. And let us say this is CP. The line of action will pass through the CP, and we can easily find out HCP. How? HCP will be equal to x bar plus IG by AX bar. This is how the vertical projection can be, horizontal component can be calculated. For vertical component, extend the edges of the curve normally up to free surface like this. The weight of the fluid which can be contained, by the curve up to free surface, that is the magnitude of Fv. This fluid will measure the magnitude of Fv. The weight of the fluid which can be contained by the curve up to free surface. The direction will be decided by actual contact Fv, and its line of action will pass through the centroid of the corresponding weight. So once we calculate FH and Fv, the resultant or the total hydrostatic force. The resultant or total hydrostatic force is under root of FH square plus Fv square. And phi, this is let us say FH, this is let us say Fv, and this is the resultant force Fr. This is angle phi. Phi will be equal to tan inverse of Fv by Fh. That is how analysis of hydrostatic force on a curved surface is done. This is fine. The last topic of hydrostatic force is buoyancy and flotation. The next topic is buoyancy and flotation. When a body is immersed in a static fluid, either completely or partially, the net upward hydrostatic force. Yes, all the measurements are from the free surface. The depth of CP from the free surface is HCP. The depth of centroid of the plane surface from the free surface is X bar. When a body is immersed in a fluid, either completely or partially, the net upward hydrostatic force exerted by the fluid on the immersed body is called as buoyant force. So what is buoyant force? Net upward hydrostatic force. That is called as buoyant force. And according to Archimedes principle, the buoyant force is equal to weight of the fluid displaced by the immersed body. What is buoyant force? That is rho of the fluid into G into volume of the fluid displaced. That is not a function of density of the body. And the centrobuoyancy is the point of application of buoyant force. Centrobuoyancy is the point of application of buoyant force, which is the centroid of the displaced fluid. Eureka, yes. Which is the centroid of the displaced fluid. When a body is immersed or floating, yes, it is independent of location and density of the fluid. For immersed or floating body, there are two conditions. Net force must be zero. We can say that implies buoyant force is equal to weight, or we can say volume of the fluid displaced is equal to density of the body into volume of the body upon density of the fluid. That is one condition. The another condition is net moment is equal to zero. For rotational equilibrium, or we can say line of action of buoyant force and weight must be same. B and G must lie in the same vertical line. B and G must lie in same vertical line. B and G must lie in the same vertical line. These are the two conditions for equilibrium. One is for vertical equilibrium, another is for rotational equilibrium. Once the immersed body or the floating body satisfies these two conditions, then we find out whether the body is stable, unstable, or neutral. For a completely submerged body, the criteria for rotational stability, I have told the students to memorize this bag. B must lie above G. If B is lying above G, then the body will be in stable equilibrium, rotationally stable. If B and G coincide, then it is neutral equilibrium. And if B is lying below, then it is unstable. Then it is unstable equilibrium. So for completely submerged body like submarine or hot air balloon, for a floating body, what you need to memorize? Meta center must lie above the center of gravity, MAG. For stability, for a floating body like a ship, meta center must lie above G. If this is the situation, then it is stable. G and M if coincide, then it is neutral. And if M is lying below G, then it is unstable. Meta center need to be located for getting the condition for stability. Or there is a term called metacentric height. What is metacentric height? GM. GM is equal to BM minus BG. That is called as metacentric height. Metacenter is the point about which the floating body oscillates. The difference between BM and BG is called as metacentric height. How to find out BM? Where BM is calculated by Ixx upon volume of the displaced fluid. BM can be calculated from this formula Ixx, that is area moment of inertia of the horizontal section of the floating body on the fluid surface. M means metacenter, A for above. This is the trick, god of thermodynamics. M for metacenter, A for above, and G for center of gravity. If the metacenter is lying above center of gravity, then it is stable. अगर बी नीचे है जी से तब ये तीन कंडीशन बनती है. उसी तरीके से पिछली स्लाइड में मैंने बोला बैक BAG centrobuoyancy must lie above center of gravity. If the centrobuoyancy is lying above center of gravity, then it is stable equilibrium for submerged body. If B is lying above G or B and G coinciding, then floating body is always stable equilibrium. Then the floating body will always be in stable equilibrium. Always be in stable equilibrium. When B is lying below G, then there are three possibilities. When B is lying below G, then there are three possibilities based on the location of metacenter. But when B is lying above G or B coinciding with G, then the floating body will always be in stable equilibrium. Then we do not require. अच्छा, आपकी ट्रिक क्या है? आप भी शेयर करिए अपनी ट्रिक, स्टूडेंट को जो कन्वीनियंट लगेगी. मदर गर्ल बॉय. अच्छा. For rotational stability, when BM comes out to be greater than BG or metacentric height is positive, then it is stable. If BM is equal to BG or metacentric height is equal to 0, then it is neutral equilibrium. Then it is neutral. Or if BM is coming out to be less than BG or metacentric height becomes negative, then it is unstable. And time period of oscillation is given by tau pi under root of Rg square upon G into Gm. Time period of oscillation, the formula for time period of oscillation. Rg is radius of gyration. Radius of gyration. There is another experimental method to find out the metacentric height. Do you know that? Gm is given by W dash into x upon W tan theta. Theta is the angle of tilt. This is the experimental method. Theta is the angle of tilt. Theta is the angle of tilt and W dash is the jockey weight which is moved by a distance x. X is the distance and W is the weight of the ship. So that completes our second part, that is fluid statics. And now we will move to the kinematics part and then we will finish today's session. I will bring another session very soon for dynamics. Let us move to the kinematics, the analysis of the flowing fluid without considering forces. Flow without forces. the analysis of the flow without forces. That is kinematics. The first topic in kinematics is the types of fluid flow. Steady and unsteady flow. Steady flow is when the fluid behavior, pressure, density, velocity, they are independent of time. At a particular section, if the fluid behavior does not change with time, then the flow is steady. And otherwise, the flow is unsteady. Uniform and non-uniform velocity is not a function of space at a particular instant. Then it is uniform. Otherwise, it is non-uniform. Laminar and turbulent are defined by the Reynolds number. If Reynolds number is low, the flow is laminar. For low value of Reynolds number, the flow is laminar. And for high value of Reynolds number, flow is turbulent. Compressible and incompressible. In case of incompressible flow, density is neither be a function of space nor time. Density is constant. That is incompressible flow, otherwise compressible. Rotational and irrotational. When the fluid particles rotate about their mass centers, then it is rotational. If they do not rotate, it is irrotational. For irrotational flow, omega x, omega y, omega z is equal to 0. 1D, 2D and 3D based on the space coordinates, based on number of space coordinates required to describe the flow. Based on the number of space coordinates. Number of space coordinates. These are the various types of fluid flow. What is ideal flow? There is the difference between ideal fluid and ideal flow. I told you the flow which should be non-viscous or inviscid or frictionless, or we can call it as irrotational. When tau is equal to 0, when shear stress developed is 0, the second condition is the flow must be steady. What is steady flow? Pressure, density, velocity at a particular section independent of time, and the flow must be incompressible. That makes the flow to be ideal flow. Incompressible. What is incompressible flow? When density is neither be a function of space nor time. Density is constant in the flow. That makes the flow to be ideal. These are the conditions for the ideal flow. These are the conditions for the flow to be ideal. Then we define a streamline. This line is called as a streamline. What is the definition of the streamline? The velocity vector and the streamline are tangent to each other. That is the streamline. It is an imaginary line drawn through flowing fluid in space such that a tangent drawn to it at any point gives the velocity of the flow at that particular point, or the line which is tangent to velocity vector at every point. So streamline and velocity are tangent to each other. So the fluid always flow. What is the velocity vector? That is given by ui cap plus vj cap plus wk cap. What is the magnitude of velocity? It is under root of u square plus v square plus w square, where u is equal to dx by dt, v is equal to dy by dt, and w is equal to dz by dt. These are the component of velocity in x, y and z direction respectively. The fluid always flow along the streamline. The flow always takes place along the streamline. So we define the differential equation of the streamline, that is given by dx by u is equal to dy by v is equal to dz by w. This is the differential equation of the streamline in three-dimensional flow. For 3D flow, for two-dimensional flow, we can write it as dx by u is equal to dy by v, or we can write it as v dx minus u dy is equal to 0, or we can write it as dy by dx is equal to v by u. That is also called as slope of a streamline. We can also call it a slope of a streamline. So the family of curves satisfying the above equations are known as streamlines of the flow. We can find out the streamline. The relation between a function between x and y is equal to constant is the equation of the streamline. By integrating this differential equation, we can obtain the equation of the streamline. Right? Then we define the continuity equation or mass conservation. Mass conservation equation for one-dimensional and steady flow. Mass flow rate entering into the control volume should be equal to mass flow rate leaving from the control volume. That is the continuity equation for one dimensional. What is the mass flow rate? That is rho into Q is equal to rho into A into V. That is the mass flow rate. Cohen streamlines are defined for the whole flow. Streamlines are defined for the flow. They are not defined for a particle. Streamline is the family of curves. And the streamlines are always parallel to each other. All the streamlines for a particular flow are drawn parallel to each other. For incompressible flow, rho is constant. If rho is constant, then we can say sigma q in is equal to sigma q out. Q is the discharge. So that is the continuity equation for one-dimensional steady and incompressible flow. For generalized continuity equation is given by, which is valid for all type of fluid flow, del rho by del t plus del by del x rho into u plus del by del y rho into v plus del by del z rho into w is equal to 0. That is the generalized continuity equation. Or we can write it as del rho by del t plus del dot rho into velocity vector is equal to 0. So the fluid flow is possible only when the continuity equation is satisfied. This equation must get satisfied. If the flow is steady, then the continuity equation is given by del x rho u plus del by del y rho v plus del by del z rho w, or we can write it as del dot rho velocity vector is equal to 0. If the flow is incompressible, for incompressible, del u by del x plus del v by del y plus del w by del z, we can call it as del dot v, that is divergent of v, is equal to 0. That is the condition, that is the continuity equation for incompressible flow. This is very, very important. Then the next parameter is fluid acceleration. Local, or there are two types of acceleration because the velocity is a function of space and time that develop the acceleration. When the velocity changes either with space or with time or both, so there is an acceleration developed that is called as local acceleration when the velocity changes with time. So the local acceleration is given by del v by del t. Then the convective or advective acceleration when the velocity changes with space. So the convective acceleration is given by v into del v by del s. And the total acceleration will be equal to sum of local, algebraic sum of local and convective. That is the total acceleration. Sum of local and convective acceleration. When the flow is steady, local acceleration will be, steady flow means v is not a function of time. Local acceleration will be 0. For uniform flow, velocity is not a function of space. So convective acceleration will be 0. For steady and uniform flow, the total acceleration will be 0. It means velocity, it means velocity will neither be a function of space nor time. Velocity is constant. That is for steady and uniform flow. That is for one dimensional flow. This is the acceleration for 1D flow. And the formula for acceleration for three-dimensional Cartesian coordinate system, we can say a acceleration vector, that is dv by dt, is equal to del v by del t plus v dot del into v. That is the expression for acceleration, or we can write it as acceleration vector as axi cap plus ayj cap plus azk cap. Magnitude of acceleration will be equal to under root of ax square plus ay square plus az square. What is ax, ay, az? Where ax is du by dt, or we can write it as del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del t del z. That is ax, ay, which is dv by dt, that is equal to del v by del t plus u into del v by del x plus v into del v by del y plus w into del v by del z. Similarly, we can write 8z, that is dw by dt, that is del w by del t local plus convective, u into del w by del t, sorry, del x plus v into del w by del y plus w into del w by del z. So we can separate them. These are the convective acceleration. This is convective. This is local. This is how acceleration is written. Another term is rate of angular deformation, epsilon, or d theta by dt. The rate of angular deformation is total rate of change of angles of initial drawn perpendicular line segments. In xy plane, epsilon xy is del v by del x plus del u by del y, or epsilon yz is equal to del y plus del z, del w, del v. Epsilon zx is equal to, here it is del z plus del x, here it will be del u, del w. These are the rate of angular deformation, rate of shear strain or strain rate, which we have discussed in Newton's law of viscosity. This is rate of angular deformation. Rate of rotation or angular velocity is average of rate of change of initially drawn perpendicular line segments. Omega about z-axis is equal to half of del v by del x minus del u by del y. Omega about x-axis half of del y minus del z, del w, del v. We can write omega about y-axis half of z minus del x, del u, del w. Or we can define the angular velocity vector. Omega vector, angular velocity vector, omega vector is equal to half of this determinant, I cap, j cap, k cap, del by del x, del by del y, del by del z, u, v, w. Or we can write it as half into del cross v. That is called as angular velocity vector. What is vorticity? Vorticity is twice of angular velocity. Tendency of the fluid element to spin or rotate, twice of angular velocity. Mathematically, it is curl of P. So vorticity vector, which is twice of angular velocity vector, is equal to this determinant I, J, K, del by del x, del by del y, del by del z, u, v, w. That is called as del cross v. That is called as curl of v, curl of velocity vector. Cross product of del and velocity vector is called as curl of velocity vector. Last few minutes. Velocity potential function is defined, that is phi, scalar and continuous function of space and time, such that its negative derivative with the space gives the velocity of flow in that direction. So fluid always flow in the direction of decreasing potential. Minus of del phi by del x is equal to u, minus of del phi by del y is equal to v, and minus of del phi by del z is equal to w. This is how the velocity potential function is defined. So the fluid flow is possible only when the velocity potential function satisfies Laplace equation, and the flow is always irrotational, and the irrotational flow is called as ideal flow, or we can also call it as potential flow. We can also call it as potential. Ideal flow or potential flow. Stream function, another function is defined psi. It is also a scalar and continuous function of space and time, which is defined such that it must satisfy continuity equation for two-dimensional incompressible flow. So value of psi increases to the left of flow direction. So del psi by del y is equal to u, and minus of del psi by del x is equal to v. This function is defined. And the property of this function is it exists for both types of 2D flow. The stream function exists for both type of 2D flow, rotational and irrotational. The flow is irrotational only when psi satisfies Laplace equation, otherwise the flow will be rotational. So about the potential function defines the flow only when it satisfies Laplace equation, and the flow is always irrotational. Whereas the stream function, the existence of stream function defines the possibility of the flow, guarantee the possibility of the flow. And when stream function satisfies Laplace equation, then the flow is irrotational, otherwise rotational. So if we equate u with u is equal to minus of del phi by del x is equal to del psi by del y. This is one equation. And v is equal to minus del phi by del y is equal to minus of del psi by del x. This is another equation. These are known as Cauchy-Riemann equation. These two equations are known as Cauchy-Riemann equation. And the velocity potential function phi is valid for 3D and irrotational only, whereas the stream function is valid for 2D flow or axisymmetric, both rotational and irrotational flow. Right? And another note is difference between any two stream function psi1 and psi2 represents discharge per unit width between the streamline. For one dimensional steady flow, psi is constant for a particular streamline. Psi remains constant for a particular streamline. So what we can say? Q is equal to psi2 minus psi1 is equal to constant. Discharge per unit width between the streamline is given by the difference between stream function. And equipotential lines and streamline, dy by dx slope for equipotential line multiplied by dy by dx for constant stream function line is equal to -1. So because the slope product of the slope is -1, so equipotential line and the streamlines are always orthogonal to each other in the flow field, except at stagnation point. What is the stagnation point? The point of zero velocity is called as stagnation point. So that is all from my side. As once again I remind you that GATE BYJU'S exam prep is providing you the GATE and ESC test series. You can purchase for the nominal price, and the test series are going to be very, very important for improving your rank. So these are my contact details. I am going to share the PDF of this session to my Telegram group. If you have not joined me on the Telegram, please do it. And I will bring another session for fluid mechanics dynamics session, formula revision session very soon. I will, all right. So the link for joining my Telegram group is there on the screen. So guys, that is all from my side. Thank you for being there. See you in the next session. And if you have anything to discuss, you can always contact me through the Telegram group, or you can write me personally through my official mail ID. All right. So take care, enjoy, have a good night, stay safe, stay motivated, keep preparing with your full dedication and hard work. Thank you guys. Thank you very much. Jai Hind.